All right, so let's begin. So today we're going to talk about load balancing. In the most canonical form, let's suppose that you're given M machines. So 1, 2, and so on. The jobs arrive one after the other. So job 1, job 2, and so on. We don't know what order they're arriving. And job I has size Wi. Now, problem is to assign each job to one of the M machines. So now, after assignment of jobs, so load on machine I let that be L of machine I. So let's call this job J. The summation of all J, where J have been assigned to machine I. So objective is to minimize the maximum of L. So this is the maximum load seen across all the machines, and by your assignment, let's call that assignment to script A, you would like to minimize the maximum across all. Is the problem clear? So jobs are arriving one after the other in online fashion. Job J has size Wj. On its arrival, you have to assign it to one of the machines. After all jobs have been assigned, the load on the machine I is just the sum of the sizes of all the jobs assigned to it. And your objective is to minimize the maximum load across all jobs or machines. Is the problem clear? So what's a trivial algorithm? So if you are given this problem, what would you like to do? Anyone?
Assign the job to any machine that has the capacity.
So there is no capacity. You can load as much as you want. You're just counting Li to be the summation of the size of all the jobs. So there is no capacity to these machines. You can assign as many jobs as you want.
Take the average weight of all the jobs, and for a particular machine, if add a job, if upon adding it the weight does not exceed the average, or go to a new machine if it exceeds an average.
Something simple can try to do what you're trying to do, right?
Assign the job to the machine with the least weight, least
Yeah,
load rate.
exactly. It's like greedy. Greedy is on arrival of, sorry, on arrival of a job, assign it to currently least loaded machine. Okay. So suppose you do that, can you give a trivial upper bound on the computative ratio of such an algorithm? Any guesses? It's not difficult to guess and prove also. The trivial one. The slightly sharper one is slightly non-trivial. So what can go wrong for such an algorithm?
So one machine gets much bigger load compared to others.
That's not possible, right? Because each time when a job arrives, you're assigning to the least loaded machine. So things can go wrong only if like one job size is large, but thereafter you will not assign that machine where this large job went for a very long time. So things are not too bad. So your algorithm is by default doing the load balancing job. That if some job is large and it went to particular machine, the later arriving jobs will not go to the same machine. So let me write and maybe you can get the job. So the competitive ratio of greedy, it's easy to see it is at most 2. Slightly sharper is 2 minus 1 by m. So this you will prove in the homework. But 2 you should be able to see directly. And then you should also show that there is a tight example that gives that it is at least greater than 2 minus 1 by. So greedy, the competitive ratio of greedy is exactly 2 minus 1 by. So 2 is what I wanted if somebody couldn't see it. Now can you see why 2 should be the right answer? It's never more than 2. Okay, so maybe I'll leave this as an exercise. It's not difficult. So the simplest setting we looked at was any job can be assigned to any machine and all machines are identical. So let's look at the most simplest non-trivial setting next, where greedy doesn't work. But now M machines, machine number 1 through M, have speeds S1 through Sm. And let's say S1 is smaller than, S2 is smaller than. That's just without, so machines are faster this way. And a job J that arrives has size Wj, and the load of job J, if assigned on machine I, is Wj by Si. Okay. Now it's slightly different compared to the simpler setting. A job on its own has a size, which is Wj, but if you assign it to a particular machine, the load it imparts depends on the speed of that machine. Okay. So similarly, load on machine I is nothing but 1 by Si summation of Wj, J belongs to N. And the objective is as before, minimize maximum with your. All right, is the problem clear how it is different compared to the simpler problem? Now you have not only that you have to worry about what is the load on these machines, you also have to worry about what are the speeds of these machines when you do assignment. So now the greedy algorithm doesn't really work very well. So greedy algorithm gives you a competitive ratio of log n, where n is the number of jobs. So you have to look at something non-trivial. So here is the algorithm which we are going to look at. Called slowest first. Okay, before we go there, is the problem clear? How different it is compared to the simpler case?
Yes.
So now throughout these lectures on load balancing, we'll assume a certain conceptual thing, and then we'll relax later. We'll assume that either we know the optimal minimum load achieved by the OPT or an upper bound delta on LOPT. We'll show that how to relax this later, that you can actually estimate this delta. But throughout maybe 3 lectures, we're going to talk about load balancing. We're going to assume that either you know LOPT exactly or you know an upper bound of delta on the LOPT. And we'll use this to define algorithms. And then we will say how to get rid of this and pay an additional penalty in the competitive ratio. So here is an algorithm. Input is speeds SI of all machines. And delta, which is as much as LOPT. So initialize load equal to 0 for all machines. Now, as jobs arrives for j equal to 1 through n, job arrival, jth job arrival. Define set of machines to be assignable. So set of assignable machines for job j. To be MA of j, where these are the indices of machines for which the current load Li plus Wj by Si, which is if you assign job j to machine I, this will be the new load on machine I, Li plus Wj by Si. This should be less than equal to 2 times delta. So if this condition is true, then you define a machine to be assignable for job j. Now if there is no machine which is assignable, you declare algorithm to fail and you break and quit. Otherwise, assign job j to the slowest machine or the machine with the slowest speed, slowest machine of MAG. So among the assignable machines, pick the machine which has the slowest speed and assign job j there. Update Lj to be equal to slowest machine of j. Let that machine be A. So let's call the slowest machine to be A. Then La is equal to La plus Wj by C. And you end your if condition. Okay, so let's go over the algorithm. It's a very simple algorithm. What it's trying to do is, whenever a new job arrives, it tries to find all the machines where this job is assignable. Where the assignable condition means that after assigning this job to that machine, does the total load remain below 2 times delta or not? Or 2 times lambda or not? If it is, then it's assignable. And among the assignable machines, it assigns the job to the slowest machine possible. If there is no assignable machine, then the algorithm says, okay, I give up and I exit. Is the algorithm clear? So it's critically using the fact that I know something about lambda. So lambda is an input to the algorithm, which is assumed to be greater than equal to LOPT. So theorem is, if lambda is greater than LOPT, then the slowest first algorithm never ends in a fail state. So as long as our upper bound is a valid upper bound on LOPT, we will actually not get into a condition where there exists a job for which there is no assignable machine. That's not going to happen. The implication of this is that load on any machine is always less than equal to 2 times lambda, because all machines are assigned, like at least one machine is assignable every time. So corollary, if lambda is in fact equal to LOPT, then the competitive ratio, this algorithm, is at most 2. Does everybody see that? What am I saying in the theorem? That if lambda is a valid upper bound on LOPT, then the algorithm which I have will never end in a fail state. And what does that mean? Someone? Guys, speak up.
Fail state is when a new job arrives and there is no machine to which it can give.
Can you speak up a bit? I can barely hear you.
Hello?
Yeah, slightly stronger.
So, fail state is when a new job arrives and there is no machine to which it can give.
So suppose I prove that every time a job arrives, I have at least one machine where I can assign this. Why does it mean that the load on any machine is at most 2 times lambda? Is the question clear what I'm asking?
So if
Maybe similar to the upper bound which we gave in the artificial case.
Sorry, I can barely hear you guys. So speak up. What is my assignment condition, remember? Set of assignable machines is all the machines for which load after, if I assign that job to that machine, remains below 2 times lambda. All I'm saying is that for every job, there is at least one machine where this condition is satisfied. Why does it imply that the load on any machine doesn't go beyond 2 times lambda?
Because we are only assigning the load if
Correct.
it's
So
not more than 2n.
exactly. So whenever I actually do end up assigning a job to a machine, that's the only time the load goes up. And I do that only if it is less than 2 lambda. So there is no machine for which the load is going to exceed 2 times lambda. And that is why the corollary follows that if lambda is in fact equal to LOPT, then competitive ratio is exactly or at most 2. Okay, so shall we proceed to proof, or there any comments to be made here, or anybody has anything to say about the algorithm? Why it makes sense to do this?
So this 2 lambda limit is before assigning a job, before assigning a new job.
No, after assign. So Li plus Wj by Si. So those are the set of machines that even after assignment, I will not exceed 2 times lambda. And that is why I can say what I'm saying. That at each job arrival, I'll assign it to some machine. Because of my assignable condition, that will ensure that the load on the machine after assignment is never more than 2 times lambda. And for all jobs, there is at least one such machine. Any other questions? So how to estimate lambda? We will do one generic theme for all the algorithms we're going to present. So I'll defer it for maybe next class, how to estimate lambdas. But for the moment, assume that lambda is given to you and it satisfies the property that lambda is greater than or equal to LOPT. Okay, so we're going to use contradiction. So essentially we'll try to see, essentially suppose on a job arrival, there are no assignable machines. Then something has to go wrong. Then we'll try to give a contradiction. All right. So slightly definition heavy, so stay with me. If some definition is not clear, ask me. So now let the algorithm encounter the fail state. That means there is no assignable machine on job J's arrival. So job J is the we are indexing is the job at which there is no assignable machine. Now consider the machines, set of machines. EJ minus 1, okay, which is equal to all machines such that Li of J minus 1, that is just before the arrival of job J, the load on machine I is at most LOPT, not 2 lambda. Okay. So in the algorithm we checked something, the comparisons are made with respect to 2 times lambda. Here I am making comparison with respect to LOPT. So this is only for the proof. So definition clear of EJ minus 1. EJ minus 1 is a set of machines whose load just before the arrival of job J is at most LOPT. And among the mod EJ minus 1 machines, among such machines, let Fj minus 1 be the fastest machine. Belonging to EJ minus 1. So Fj minus 1 is the fastest machine among all the machines in set EJ minus 1. So you should definitely ask, what if EJ minus 1 is empty? Then we define Fj minus 1 to be 0 without loss. Okay, so lemma, first lemma, that Fj minus 1 is strictly less than M. So M, remember, is the fastest machine. What we are trying to claim is that the fastest machine among the set EJ minus 1 is not, it's definitely a machine which is slower than the fastest machine. So anyone wants to prove this? It's not a difficult proof. Remember, J is our job that was unassignable. And EJ minus 1 is a set of all machines whose load just before the arrival of J is at most LOPT. So if Fj minus 1 is equal to M, you should be able to get something wrong. So suppose Fj minus 1 is in fact equal to M. So what does it mean? That machine J minus 1 belongs to set EJ minus 1, and which means that Fj minus 1. So this means that Fj minus 1, J minus 1 is less than LOPT by the definition of set EJ minus 1. Everybody with me so far?
Yes.
Okay. Now, moreover, what else do I need? Because M is the fastest machine, what can you say about LOPT and WJ divided by SM? Can you compare the optimal load and the load put by job J on the fastest machine? Can you compare these two quantities? See, each job has to be assigned somewhere by the OPT.
LOPT less than equal to WJ plus.
Opposite, right? See, this is the least load optimal algorithm will exert for job J, WJ by SM, because SM is the fastest machine. Anywhere else you put it, it's only going to be larger. And LOPT is the max over all machines. So LOPT has to be greater than equal to WJ by SM. Is this point clear to everybody? This is important. This will show up everywhere. That you look at any one particular job and look at its load on the fastest machine. LOPT is always larger than this quantity. So now let this be 1 and let this be 2. So if you combine 1 and 2, what does it mean? So this, remember, is equal to M. Okay. So all it tells me is that Lm of T, so J minus 1, plus Wj by Sm is at most 2 times LOPT. Correct? And given that lambda is greater than LOPT, this also implies it is 2 times lambda. So therefore, job J would be assignable on the fastest machine if Fj minus 1 was equal to M. And this we know is not true, because job J, in fact, to begin with, is not assignable on any machine, and in particular the fastest machine. Fj minus 1 is strictly less than M. Should I go over this again, or is it clear what happened? The claim we want to prove is that among the set of jobs Ej minus 1, the fastest machine is not the fastest machine among all possible machines. So Fj minus 1 is strictly less than M. That is what we wanted to prove. The proof idea was that suppose Fj minus 1 was in fact equal to M, then we know by definition that Lm of j minus 1 is less than LOPT by the definition of Ej minus 1. And we also know that Wj by Sm, that's the least load exerted by job J on any machine, is less than equal to LOPT. And if you combine equation 1 and 2, you get that the Lm of j minus 1 plus the new load is at most 2 times delta on the fastest machine. So job J should have been assignable if Fj minus 1 was equal to M. And given the fact that we are starting with that job J is not assignable, Fj minus 1 has to be not the fastest machine. So you can think of it in terms of 1 to somewhere this Fj minus 1 exists. This is my fastest machine. And this is strictly below this. Okay. Increasing speed. Any questions? Okay, more definitions. Okay. Define O to be set of machines which are overloaded. That is I such that Li of j minus 1. J minus 1 again is the time just before arrival of job J greater than LOPT with I greater than Fj minus 1. So we are looking at machines in this regime for which the load just before the arrival of job J minus 1 is greater than LOPT. So small proposition. Can somebody say why O is not empty? If you understand the definition of O, it should be obvious why it is not an empty set. and our previous proposition which showed that fj minus 1 is strictly less than m. So what is fj minus 1? ej minus 1 is a set of all machines whose load just before job j's arrival is less than LOPT. And fj minus 1 is the fastest machine among all of them. So when you're sitting at fj minus 1, all machines to the right have this property true. That's just by definition. And what we have proven already is that fj minus 1 is not m. So there is a non-trivial set which is O, and O is not empty. Is this clear? What fj minus 1 is?
Yes.
So fj, yeah. So any machine which is on the right hand side of fj minus 1 necessarily has load which is greater than L times OPT, LOPT. And because fj minus 1 is not M, the set O is a non-trivial set. Okay, so now among, always remember we are anchoring at the jth job which was not assignable. So J is very important one. So among the first j minus 1 jobs, let Si, so this is capital S, and SIOPT be the set of jobs assigned to machine I by the algorithm and the OPT respectively. So I'm only looking at the jobs that have arrived so far before job J. And I'm just seeing an allocation. It could be arbitrary. We don't know what it is. So among all machines, look at SI as the set of jobs assigned by the algorithm, and SIOPT is the set of jobs assigned to machine I by the OPT among the first j minus 1 job. So now consider the following quantity. Can somebody make sense of this? What is this quantity? Remember, SM is the fastest machine. So speed of the fastest machine. So I'm looking at all jobs. So this is nothing but set of jobs belonging to union I belongs to code. That's another way of writing this. So I've defined a set O, right? With respect to that, I'm now checking among the set O, look at all the jobs that are assigned by algorithm to it. So that is what this, so this is the load, this quantity is the load exerted by all the jobs which are assigned to machines in set O by the algorithm divided by the speed of the fastest server. So it's as if you take the algorithm's prescription. So algorithm is, let's say, these are the set of machines O. So let's go. Starting, so this is fj minus 1. This is my O. I'm looking at all the jobs assigned to O, and suppose all of them were assigned to the fastest machine. Just move it there. What would be the load? That's what I am essentially doing. Because I'm dividing it by the speed of the fastest machine, that is precisely what is going on. Is this clear? So this is the algorithm. And I'm looking at the set of jobs which are assigned to machines in O. I'm looking at their perceived load if I were to assign all these jobs to the fastest machine. And that is why I'm dividing this quantity by Sm. Is this clear what I'm trying to do?
Yes.
Okay. So now we're just going to rewrite in many different forms. So I belongs to O, K belongs to Si, Wk by Sm divided by Wk by Si times Wk This is just rewriting, nothing non-trivial going on. So this is also equal to, I'm breaking this summation over two sides, SI over SM. So that is the speeds. I'm summing over all jobs. So WK over SM. This is again just by. Now, what can you say about this quantity?
It is the load of machine I. SI.
Yes. Can you lower bound it somehow? Remember, I belongs to O. And O definition of O is that they are all overloaded machines. So Li of j minus 1 is greater than LOPT. So how much is this quantity? You're right that this is the load of machine I, where I belongs to O. And by definition of O, this quantity is greater than LOPT. Everybody agrees?
Yes.
That's all. So I'm just making very simple improvements to what I'm trying to do using my definition. So now look at this very carefully. The next step is also not that difficult, it's just that it's not obvious. Once I write it, it should be easy. SI by SM. Now I'm going to look at SIOPT. K belongs to SIOPT. WK by SI. Why is this true? Essentially, I'm saying that LOPT is at least greater than this quantity. So just this quantity, LOPT is greater than this quantity. This quantity is nothing but the load assigned by the OPT on the ith machine. And that by definition, LOPT be at least as much as this. Right? Whatever LOPT, sorry, whatever OPT assigns to any machine, the optimal load cannot be less than that load. And this is just the load on machine I with OPT. So that is clearly smaller than LOPT. Now I just multiply and divide to get I belongs to O summation K belongs to SI OPT WK over SI. So where did I start? I started with, on the left hand side, with summation WK over SM, where the sums over I belongs to O and K belongs to SI. And I've been able to compare with K belongs to SIOPT. So what does this mean here? Now let's multiply and divide by SM. So multiplying and divide SM, we get that summation WK I belongs to O, K belongs to SI is less than equal to I belongs to O, K belongs to SIOPT, WK. Okay, can somebody say what does this mean? That the sum of the sizes of some jobs is less than sum of the sizes of jobs on the right hand side. What can I deduce from this? Remember, SI is the set of jobs assigned by algorithm to machine I, and SIOPT is the set of jobs assigned by OPT to machine I. That's the only difference between left hand side and right hand side. And this is strict. Can somebody interpret the left hand side and the right hand side? That there lies the answer, essentially. What is the left hand side? Someone? Is it not clear what the left-hand side is?
Sum of loads of machines in set O, like as given by the algorithm.
That's all. And on the right-hand side, it is done by the OPT. Now, the fact that this is greater, what does it tell you? That there is some job which has been assigned by algorithm to this set I belong to set O, which has not been assigned by the OPT to set O. That is essentially what it means. And also remember, suppose the machine I belongs to O, let's say I1, and I2 doesn't belong to O. What can you say about their speeds? What is SI1 compared to SI2? Remember our picture here. Yeah. So O is the set of machines which are to the right of the Fj minus 1. Now, if some machine lies outside of O, that means that it is to the left. That is slower speed. So SI2 is slower than SI1. So this also we know. So now can somebody say what this means and use this fact? So there is at least one job which has been assigned by the OPT to the set of machines O, which has not been assigned by the OPT to the same set of machines. And we know that if the machine lies outside of set O, its speed is smaller than the set of machines lying inside O. That is what I mean by SI1 greater than SI2. So this implies that there exists a job, at least one, assigned by the algorithm to some machine in set O, that is assigned by OPT to a machine, let's say R, which doesn't belong to O, and in particular which is slower than any machine of set O. See, this is important because remember our algorithm chooses among all assignable machines the one which is the slowest. So that is what we are trying to argue, that at some point of time, given that this job J is unassignable to any machine, there must be some other prior instant at which a job must have been assignable to a machine which is slower than the machine which the algorithm used. So that is what we are trying to do. And this is one step in that direction. Is this assertion clear that given equation number 3, I can say that there exists a job assigned by the algorithm to some machine in set O that is assigned by OPT to some machine outside of O, and that machine R has a speed which is slower than any machine of set O. Now OPT allocates, so let this job be J prime, job J prime to machine R. That's what it did. Then therefore Wj prime by SR must be less than LOPT, which is less than. Again, if the OPT is assigning a job to it, then the load seen on that particular server has to be less than equal to LOPT. Now, by definition, Fj minus 1 is the fastest server, the machine, among the set O complement. That's just by definition. Therefore, what we have is that fj minus 1 is indexed to the right of r. And essentially s of fj minus 1 is greater than s of r. So now using phi, we can also say that wj prime divided by sfj minus 1 is also less than LOPT. A job j prime is among the first j minus 1 jobs. Therefore, the load now we can write this as well. I will explain this one. Okay, can somebody say why this is true and then what this is true? Where remember L of fj minus 1, fj minus 1 is the fastest server. So L fj minus 1 is just the index of or the load of the fastest server of set ej minus 1 at time j minus 1. Now we're comparing that the same server at a previous time j prime minus 1. See that the load can only increase over time. No jobs are disappearing over time. Okay. So as time increases, j prime is a job which appears in the first j minus 1 jobs. So this quantity A is less than equal to B is trivial and B is less than equal to C. Why is that? Anybody remember our definition of fj minus 1? So ej minus 1 was a set of servers I such that Li of j minus 1 was less than equal to LOPT and fj minus 1 was the fastest server machine from set ej minus 1. So C follows. So B is less than equal to C just by the definition of ej minus 1. Am I losing you guys? Just let me know here. Which part is not clear? Silence is pretty bad. Hari, is it clear?
The first inequalities.
Can you speak up a bit? Sorry.
Hello.
Yeah,
The first inequality is not clear.
it's not clear. So what is J prime? J prime is a job which is one job among the first J minus 1 jobs. And what is the time J prime minus 1? Just before the arrival of job J prime. And as jobs arrive, they stay in the system forever. Correct? So
Yeah.
load on a particular machine only increases, it never decreases. And the fact that the time j prime minus 1 is less than j minus 1, that inequality is true. And between B and C, that is just by the definition of ej minus 1. Is it clear now?
Yeah.
Oh. So now we have 6 and 7. So what can we essentially do? We just combine 6 and 7. So now we can say L f j minus 1 j minus 1, or rather j prime minus 1 plus wj prime divided by sfj minus 1 is less than equal to 2 times LOPT. This is just trivial. I'm just using 7, the A part of 7 and 6. I'm just adding this quantity to this quantity. Essentially load just after the arrival of, so this is the load just after arrival of job J prime on machine fj minus 1. Okay, so what does it mean? That job j prime is assignable on machine fj minus 1. But remember from our earlier deduction that this job j prime was assigned by algorithm to some machine in O. What we have shown is that this job j prime is also assignable to some machine in ej minus 1 itself. So by deduction, what we have done earlier is job j prime has been assigned by the algorithm to some machine in O, which is faster than fj minus 1. But this is now telling us, while 8 is telling us that job j prime was assignable to fj minus 1. That's what 8 is telling us. And now by the definition of the algorithm, and given that any machine in O is faster than fj minus 1, we get a contradiction. So what has happened? By the deduction, we know that this job j prime was assigned to some machine in O by the algorithm. By alternate means, we have also shown that this same job j prime was assignable on machine fj minus 1 whose speed is slower than any machine in O. By the definition of our algorithm, if there are two machines to which a job is assignable, the algorithm will assign the job to the slower of the two machines. So this essentially gives us a contradiction that given that there is a job j which is unassignable, we will be able to construct another job j prime where the algorithm assigns it to a machine which is among the two machines where it is assignable, it is assigning it to the faster job, which is not allowed by the algorithm. So this assertion to begin with must be false. Praveen, is this clear? What happened here?
Yes, sir.
I'm happy to go over it if something is bugging you. There are lots of definitions, so don't get lost in definition. At least conceptually, it should be clear what we are trying to do. So we looked at a job which was unassignable with the algorithm. We looked back in time and tried to find some other job j prime which was assigned by the algorithm to some machine in O, which are overloaded machines, set of overloaded machines. We also showed that the same job is assignable to a machine which is slower than any machine in O. And the fact that the algorithm actually chose the faster machine to assign it tells us that something is wrong. That is all we have done. Arge, is this clear? Comfortable? Ranshu? Hari?
Yes.
Everyone on board?
Yes.
Okay, very good. Any comments? So as I said, we still need to estimate. So one thing which remains is how to estimate lambda. So that we will do one shot for all the algorithms we're going to present. So right now I'll defer it. But modulo that, you can actually get an algorithm whose performance is too competitive essentially, which is a very simple algorithm. Doesn't do much. So for the moment, we looked at permanent jobs. The jobs are not departing. They're just arriving and sitting in the system. Now let's look at the more interesting setting where jobs are temporary. What does it mean? That a job J arrives at time Tj and departs at time tj. Sorry, let's call it aj dj. Now dj is not under your control. It doesn't depend on what allocations you make. So dj is not dependent on assignment algorithm. So and unknown, and dj is unknown. All the algorithm knows is once it departs, the algorithm is made aware of it. So both these facts are important, that you can't control when it leaves, but you also don't know when it leaves. But once it leaves, the algorithm will get to know. That is, it will update the current load on the machine. All right. So job J has size Wj. And for the moment, assume that speeds are all 1. So S1 is equal to S2 is equal to Sm. But there is a machine restriction. That is as follows, that for a job J, among the set of machines 1 through M, there is only a subset which can process, which is defined by Mj. So as whenever a job J arrives, it can only be assigned to any machine in subset Mj, which is not necessarily the full set. So that's the extra machine restriction. Speed of all machines is equal to 1. And jobs are temporary. So that's the difference from the previous model. Is the setting clear? So load on any machine as before, load on any machine is equal to the sum of, so now time is important. At time t is summation of all jobs j which are active, load on machine I. AITWJ, where AIT is a set of active jobs. By active, I mean ones which are not, they have arrived but not departed at time t. So now this maximization is also over time. So max over all machines 1 through and time Li of t, and you want to minimize this with respect. So now there is a time component to it, which really you can't control. But you still want to minimize the maximum over all machines and over all times. Is the problem clear?
Yes.
Okay. Can you give a non-trivial example to show that a constant competitive ratio is not possible here? So you can play around with MJs, this restriction on the set of machines which a job J can be processed at. You're allowed to construct whatever you want.
OPT is also restricted to use those MJs.
Correct. But knowing the jobs which are coming in the future, OPT could change allocations. That's the power it has.
So we can assign some lightweight jobs which can take a very long time.
See, that is not under either your control or OPT's control.
No,
Time
like
is not the thing to play with. What you have to play is that which job can be assigned to which machine. So MJ can be selected intelligently by you. By you mean an adversary.
okay. So time is also not adversaries.
Time is not adversary. You don't have to worry about that being adversarial. If you want, you can. I don't mind. But that should not help you too much.
We could have like for item 1, MJ is only 1.
Yeah.
Item 2, MJ is 1 and 2.
Yeah.
Like that.
Shouldn't it be opposite? That first item can be assigned to two of them possibly. And whichever one you pick, I'll give you the next item, which can be only be assigned to that item. So you have to unnecessarily overload. So it should be the opposite
Yes.
of what you said. So M1 should be, let's say 1, 2. I'm just giving one example. And M2 is depending on what you did. So job got assigned to, let's say 1, then M2 is just 1. So now you have no choice. You have to assign the second job also to M1. Now you have to construct many more to show that. So this is in a very simplistic setting how you will construct MIs. So what you can actually show is that the competitive ratio of any algorithm is at least square root n, which is very bad, not bad, m, where m is the number of servers. So it can be as bad as square root m. So you can now think about how to get. It's not a trivial thing to get to square root m, but at least you should be able to show that it is not a constant. That is not that difficult. So the algorithm we are going to look at, so the algorithm we are going to present will have a competitive ratio of square root 2 times square root m plus 1. I'm not wrong. Yeah. So that is what we will show. So up to a factor of 2, that will be optimal. And the algorithm's name is Robin Hood for obvious reasons. We will define poor and rich machines and keep assigning things to poor machines as long as possible. Okay, so now let's say Li of t is the load on machine I at time t. See, I don't really have to worry about all times. The only times of interest are either a new job arrives or a job departs. So you can equivalently think of time in terms of only these, either a new job has arrived or a job is departing. Otherwise, there is no change to the loads. So now an algorithm will maintain an estimate called L of t. So for the moment, it is just some threshold. A machine is defined to be poor if a machine I is defined to be poor if Li of t is less than square root m times L of t and is rich otherwise. So machine is either defined to be rich or poor depending on this estimate L of t and multiplying that by square root m times. So that's the inflation factor. So if a machine is rich, if a machine is rich at time t, see everything changes with time, okay? Then its windfall time, or the time at which it essentially became rich, its windfall time is defined to be the epoch at which it became rich. So the windfall time is, let's say W, then between time W to T, machine remains rich. Essentially at W, just before W, the machine was poor, it became rich at W, and then thereafter until time T, the machine is rich throughout. Okay, so now here is the algorithm. Assign job 1 to any arbitrary machine of capital M1. M1, remember, is a set where job 1 can be assigned. And let define L of 1 to be W1. Okay, this is capital W should be, let me more import. So this is my size W. So LT, remember, is an estimate I am going to keep. So L1 is equal to W1. Now I'm going to update this estimate on arrival of a new job J at epoch or time T. L of T is going to be the following. Max of 3 quantities. L of T minus 1. How much it was before. Never go below that. The size of the newly arrived job. And 1 by M times Wj plus Li of T minus 1. I from I equal to 1 through M. So last quantity is essentially the total weight in the system after Wj's assignment divided by all the machines in the system. So this is average load per machine. So there are 3 quantities which are used to define L of T. L of T minus 1. So don't go below what you had before. So it is at least as much as LT minus 1. The second quantity is just the size of the new job which has arrived, Wj. And the third is the average load per machine after assigning Wj. Okay. So now the rich and poor, remember, rich if Li of T is greater than or equal to square root ML of T, and poor otherwise. Because L of T changes, the machine can become rich or poor as time progresses. So some machine which was poor in the past can become rich thereafter. So final assignment for new job. So assign job J to any poor machine of Mj. If there is no poor machine, assign to a rich machine of Mj with the most recent windfall time. So the algorithm would like to assign jobs to poor machines if possible, but if there are no poor machines, then among all the rich machines, find the one which became rich the most recent and assign the job there. So thereafter, update the load to, so suppose the chosen machine is Aj, so L of Aj is equal to L of Aj T minus 1 plus Wj. Okay, is the algorithm clear? It's maintaining some estimate of what it thinks is the right way to allocate, which is defined as capital L of T. Depending on that, it's defining a machine to be rich or poor. And when a new job arrives, it tries to assign a job to the poor machine, any poor machine, and if there are no poor machines, to that rich machine which became rich the most recent. That's all it means. So simple question, how many machines can be rich at any time? See, total M machines. A machine is rich if Li of t is greater than square root M times L of t. So can somebody say how many machines can be rich at any point of time? And L of t is greater than equal to the average load per machine. So how many machines can be rich at any point of time?
At most root M.
Yes. And the reason for that is that what is the total load in the system at time t? By definition, it is at most is less than equal to M times L of t. Just by definition, LT is greater than the average load. So the total load is at most M times L of t. And a machine is defined to be rich if it exceeds square root ML of t. So just by pigeonholing, there cannot be more than square root M. So there are at most square root M rich machines. Okay. Now, simple lemma. Claim is that LT is always less than equal to LOPT. So this is true on the first job arrival because L of t is just L of 1 is equal to W1, which is clearly less than equal to LOPT. So assume that this is true for some time t. We'll try to do it for next time. That this is true. So then what is L of t? L of t is max of L of t minus 1 comma Wj, which arrives at time t, and 1 by M Wj plus the total load in the system. I going from 1 through M Li of t minus 1 t minus 1. Right? So that's my L of t. Okay, can somebody help me how to show this now? So I know that L of t minus 1 is less than equal to LOPT. I want to show that L of t is also less than equal to LOPT. So this clearly is less than LOPT. I just need to show that this is also less than equal to LOPT. And why is that true? Because OPT also has to assign all these jobs somewhere, and this is nothing but the, so you can think of this as the total load in the system at this time, which the OPT can equally divide among the M possible machines. So this third term also is at most equal to LOPT. So this implies that L of t is less than equal to LOPT. So now we are ready to prove the theorem that the competitive ratio of Robin Hood is 2 times square root M. Any questions?
Yeah, so we showed that there are at most root m rich machines
Yeah.
at any. So there are always at least m minus root m poor machines.
Yeah. Okay.
So why do we need a case when there are no poor machines in the algorithm?
No, it doesn't. So among MJ, right? So we are not saying among MJ which is poor and which is rich. See, a job J arrives, it can only be assigned to one machine in MJ. We have no
Yes.
clue how small or how large MJ is. Does that answer your question?
Yes, yes.
Okay. Okay, so proof. What we are going to show is that for any machine I and for any time t, we are going to show that this is at most square root m times L of t plus LOPT plus LOPT, which combined with the previous thing that this is at most LOPT implies that Li of t is at most 2 times square root m plus 1 times LOPT. So this is what we want to show. So is 9 true for a poor machine? So by definition of poor machine is Li of t is less than equal to square root m times L of t. 9 has only few more terms. So for a poor machine, 9 is always true. So I only have to worry about showing 9 for a rich machine. All right. Everybody with me? Hari?
Yeah.
Okay. So now
Yeah.
focus on rich machines only. So consider any rich machine. R at time t. And let SR be the set of jobs assigned to it after its windfall time. See, windfall time, remember, is the time at which it became rich and has remained rich until this time t. So that's the windfall time. So now for this rich machine R, we're saying let SR be the set of jobs assigned to it after its windfall time. Now since machine R is rich throughout, let's say the windfall time T0, throughout T0 to T. Therefore, all machines in MJ without R must have become rich before time T0. Let J belongs to S. So what am I doing? I'm looking at a rich machine. I defined SR to be the set of jobs assigned to it after its windfall time. I'm going to look at any one particular such job, which is J, which belongs to SR. Now this machine R is rich throughout the time T0 to T. And given the fact that J has been assigned to SR, J has been assigned to rich machine R, it must be that all other places where J could be assigned, which is MJ, other than R, must have become rich before time T0 from my definition of the algorithm. That if I'm assigning a job to a rich machine, that rich machine also became rich the most recently. That is just by the definition of it. Is that okay? That why MJ without R must have become rich before time T0 because of the choice of job J being assigned to rich machine R. let K be the number of machines to which any jobs of SM could be assigned. Essentially, K is cardinality of MJ. J belongs to SR. Moreover, since at most square root M machines are rich, claim that K is less than equal to square root M. Can somebody say why? Why is K less than equal to square root M? See, SR is the set of jobs which have been assigned to this rich machine after it became rich. Our algorithm always chooses to assign a job to a poor machine if possible. But given that it's assigning a job to a rich machine, all options it had were rich at that point of time for any of the jobs belonging to SR. Does it make sense? Any job belonging to SR, set SR, has all its option MJ to be rich whenever it arrived because it is getting assigned to a rich machine. And the total number of rich machines is at most square root M. So K has to be at most equal to square root M. Is this fact okay? This is just a simple fact from the definition of set SR. Pranshu, is this fine?
Yes.
Okay. Now let Q be the job that arrived at time t0 that made machine R rich from poor. So remember, t0 is the time is the windfall time. That is the time exactly at which machine R is becoming rich. So let the job which arrived at that time be indexed as Q. So what we know is this is always true, that every job has to assign somewhere. So WQ is always less than equal to LOPT. Moreover, WJ, J belongs to SM, 1 by K is also less than equal to LOPT. So this is the all jobs, and they can be assigned at most K different places. So the average load at least has to be less than equal to LOPT. So now let's look at the load on machine R at time T. This is equal to LR of T is equal to LR of T0 minus just before it became rich plus WQ, that is the job which made it rich. So that was assigned. So the weight went up, load went up by WQ plus all the jobs which have been assigned since. Is this okay to everybody? So we are at time T. T0 is the time at which it became rich. SM is a set of jobs which have been assigned thereafter. And Q is the job which arrived exactly at time T0. So now I claim that this is at most LT0. Can somebody say why? What is the status of this machine at T0 minus?
It's poor.
It's poor. So just by definition of the poor, this is true. That LR T0 minus is at most square root M times LT0. Now this quantity, as we said, is less than LOPT. This is less than K times LOPT. This is as it is. Okay, and now k is at most square root m. That also we have seen. All right, so now am I done or do I need to do something else?
You need to show LT0 minus is LOPT. It's less than.
Yeah. No, I just need to show that this is L of t, not LT0. See, what did I want to prove? L of t I know is already at most LOPT. So remember, equation number 9 is what I want to show. I want to show that Li of t is less than or equal to square root m times L of t plus LOPT plus LOPT. So what do I need to show further? That this quantity is at most L of t. And why is that?
L of t is increasing with time,
Not necessarily.
not decreasing.
Why do you say so? Suppose between time t and t times 200, all jobs disappeared.
Because
You're
L of,
right, but yeah, L of t is a max of L of t minus 1, comma, the size of the new job and the average weight in the system. So it's at
yes,
least, so LT0 is non-decreasing is clear. But I don't need this, right? LT0, this itself is L of t. What I proved is this is LOPT for all time t. So in particular, L of T0, LT0 minus is less than LOPT. So we have shown this, right? So specific, making it a special case at t equal to T0 minus, we get what I want. You're right what you're saying, that L of t is a non-decreasing function, but I don't need to use that. I've already shown that for all time t, LT is less than or equal to LOPT. So in particular for time t equal to T0 minus. So the lemma is proved, and so is the result. All right, perfectly on time.